Continuing our discussion of differential equations and transforms, now I want to talk about Fourier series and transforms. So firstly, the Fourier transform and Fourier series are closely related topics, and in particular, a Fourier series states that any periodic function can be written as the sum of an infinite number of sinusoidal terms, which are sometimes called harmonic terms or harmonics. And the definition is given in this extract here, and I've rewritten the equation here. The Fourier transform f of t is equal to, the Fourier series, I'm sorry, f of t is equal to a0 plus the summation from n equals 1 to infinity of an cosine, etc., where t is equal to 2 pi over omega 0 is the period of the function, and the coefficients an, etc., are obtained from these expressions. A0 equals 1 over t, integral from 0 to t of the function of t dt. An is 2 over t f of t cosine n omega 0 t, and bn is 2 over n integral f of t sine n omega t. And furthermore, if the Fourier series representing a periodic function is truncated after a term n equals uppercase N, the mean square value of the truncated series is given by Parseval's relation. Now, normally we won't be computing Fourier series, and there are several typical series which are given in the handbook. The first one is this rectangular waveform here of amplitude V0 and period capital T. The terms in the Fourier series are given by this expression here. Summation from n equals 1 to infinity, minus 1, etc., where n are just odd numbers in that summation. The next one is a somewhat similar looking function, rectangular waveform, and the Fourier transform is given by this expression here. And finally, the last example they give is the Fourier transform of a series or a train of impulses or delta functions separated by a period or a time interval, capital T, and the Fourier transform, or the Fourier series rather, is given by these expressions here. So let's do an example on that. The question is, what is the first term of the Fourier series of the rectangular voltage function with an amplitude of plus minus 2 volts and a period t of 1 second? Which of these alternatives is the first term? So here's the situation. This is the rectangular wave train, and the amplitude varies from plus 2 volts to minus 2 volts, and the periodicity here is 1 second. So from the previous table on the previous slide, we have the general term in the Fourier series is minus 1 raised to the n minus 1, etc. So in this case, we're only asked to evaluate the first term. So first we can compute the frequency, the angular frequency, omega 0, which is 2 pi over t. And in this case, the period t is 1 second, therefore omega 0 is equal to 2 pi. So the first term then, putting n is equal to 1, we have minus 1 raised to the 1 minus 1 is 0, so minus 1, any number raised to 0 is 1, times 40 over n pi, and n is equal to 1, at cosine n omega 0 t, and n is equal to 1, and omega 0 is equal to 2 pi. So combining those together, we find that the first term is equal to 8 over pi cosine 2 pi t, and the answer is A. Now, closely related to this is the idea of a Fourier transform, which is also very important in a wide range of engineering and physical problems, especially in terms of solving partial differential equations, spectroscopy, signal processing, image processing, and many more. The Fourier transform is defined as transforming a function of time, t, into a function of frequency omega. And the definition, which is given in the extract here, is f omega of omega is equal to the integral from minus infinity of the function of time multiplied by e to the minus j omega t dt, where j is the square root of minus 1. And this is called the Fourier transform, and the reverse of this, lowercase function of t in terms of the Fourier transform, is given by this expression, and that is called the inverse Fourier transform. So these two functions form a Fourier transform pair. And some examples of applications of this are given in the extract from the reference handbook right here. So here again is the definition of the Fourier transform and its inverse from the handbook. And in the handbook, they give you a number of transforms of various functions which can be used in various situations. And one thing I'll mention about this, it uses this term sinc, or S-I-N-C, and the definition of sinc of x is sine x over x, although I don't think this is specifically stated in the handbook. So from this table, you can evaluate the Fourier transforms of various functions, and it seems unlikely that they would ask you to compute one from first principles. It also gives a number of transform theorems. For example, linearity, the first one here, the Fourier transform of the sum of two functions which are added together is simply the sum of the Fourier transforms. And effects under scale change or time change, etc., are all given here, so they can be looked up in order to use any particular transform. So that completes the discussion of Fourier transforms and series.